If you have any questions about the exam, please ask them, stop by, I'd be glad to talk with you about it. I'm going to do handout on mass spec. Our main spectroscopy test 3. And we have resonance and chemistry of dienes. Okay, we'll start here. Which amino group of the above compound is most electron rich? Can someone get this? Anybody have Andrea? The bottom one? Most electron rich? Why do you say the bottom one? How many resonance structures were you able to draw from the bottom one? Only 2 additional ones? Do what? Well, the major one's going to be the one shown because all the others are going to have charge. How many additional resonance structures were drawn from the bottom one? 1 additional for the bottom? How many do you have drawn?
I was thinking this was the first oxygen test, but I don't know.
How many resonance structures? How many resonance structures? 5 additional?
4 additional.
How do you know there's 4 additional?
I'm in bonds.
Okay.
That's on different papers.
All these questions are answered by showing resonance structures and considering the blend, the high group. Who has all resonance structures drawn for these 2? Anybody? Okay. Let's look at chemistry of dienes. The nomenclature. Comment on terpenes and terpenoids. Terpenes, anybody ever heard that term? Terpenes are natural products that occur in nature. Lots of compounds are terpenes. Retinol, retin-A, okay? Taxol, menthol. These are all terpenoids because they come from terpene. Well, they're called terpenes. Terpenes come from isoprene. This is isoprene. It's also known as 2-methylbutadiene. But it's a building block. Nature uses this as a building block very often to build these molecules. That's 5 carbons. Limonene, which you find in lemons, has 10 carbons. That's where this dimerized, 2 molecules came together. We did alkene dimerization or polymerization. There was a question on the test. Very bottom of page 2, I think. Okay. It's amazing how nature can make these molecules. The terpenes come from isoprene. Take a look at that. Y'all know Taxol. This is a dark picture of the yew tree. It's a huge tree with lots of sprawling limbs, and they're cutting there. But a tree makes Taxol from isoprene. Okay, let's look at the chemistry of dienes. We're going to look at 1,2 versus 1,4 addition. 1,2 addition is nothing new. We've been doing this for a week now with alkenes. How can we get that product? Well, it looks like we've added an H to the end and a Br there. Looks like we've been in an addition reaction with HBr. Mechanism, we got H plus and Br minus. We can show it ionized. These electrons hinge away and go attack the H, and we get carbocation, right? How do we then get final product? Br minus adds to the cation. There you go. Okay? It's like we ignored that double bond over there. This is called a 1,2 addition. Why? Because the H is on that carbon, we can call it 1. Not because of nomenclature, but just we start with 1. If that's 1, where did the bromide add? The second carbon, the 2 carbon. So we said the HBr added 1,2. That's a 1,2 addition. Now, for this example, that occurs at cold temperature, -78. That's dry ice, acetone temperature. This is called the kinetic product. We'll better define that as we move forward. Now, if you do the same reaction, but you heat it up 40 degrees or higher, approximately, you get a different outcome. The HBr, let's see, where's the new H? Well, there's 2 on the end. Now there's 3 on the end. The new H is there. And the Br is obviously there. And if that's 1, what do you want to call that carbon? 4. So this is not a 1,2 addition, but a 1,4 addition, we call that. Now, how did the 1,4 addition take place? By the way, I mentioned yesterday at the end, this Friday at 11, we're going to have an information session to talk about the new medicinal chemistry program, medicinal chemistry courses which you can take after Organic 2, chemistry. Also to talk about the Prestige program for teacher education. If anybody is interested in being a teacher, there's a big scholarship to go with that. Combined BS and MAT in 5 years. Info about both of those things on Friday at 11. Science Hall 1002, the Bring Me on the IR lecture in. And I'm offering 5 points extra credit for attending this Friday at 11 to 12. If you cannot attend, there will be some type of makeup. Like a 20-page essay on 1,4 additions or something. Okay? Maybe only 2 pages. Okay, Friday 11, yay? Okay. So how does the 1,4 addition take place? Well, it's the same thing, except we consider resonance. There's a resonance structure, correct? Windshield wiper? Move electrons over? Now we have that, and cation there. Now how do we get final product? Br minus adds to the cation. There.
I think you lost a carbon.
Am I missing carbons? It looked funny. It looked funny. Yes. I should have looked closer. 1, 2, 3. What are we missing here?
The first one.
It's drawn in that dang H that's not good. Let's do this again. There's the H, boom, 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 boom. We windshield wiper it over so it's now there. And the plus is there. Br minus adds here, and we get that. The outcome depends on which cation it adds. If the Br minus adds here, you get the 1,2 product. If the Br minus adds there, you get the 1,4 product. Because the cation is conjugated, sometimes this is called conjugate addition. Because this outcome came because of the conjugation of the pi bond, where the 1,2 is often called direct addition. We've been doing direct additions for a week. Okay? Now, this is just one species, right? What's the true species look like? Isn't it partial bond, partial plus, partial plus? That's the blend. And so you only get one intermediate. It all depends on, does the Br add here or here? Both carbons are electrophilic. Which one does it add to? Now, of course, this is cumbersome to work with. We work with the two fake structures. Questions about 1,2 addition, 1,4 addition?
So 1,4 still has only one intermediate.
It has what?
Only one intermediate, or is there two intermediate?
Both of these mechanisms only have one intermediate. It's right there. That's one intermediate, right? I mean, there it is in real life. That's the true intermediate. Where does the Br add? Okay, top one's called kinetic product. This one's actually called the thermodynamic product. Why? Because this is more stable. That's more stable than that. Why? Why is this one more stable? More substituted. That's a disubstituted alkene. That's a monosubstituted alkene. That's more stable. Thermodynamic product. Why is that called the kinetic product? Because it's formed fastest. And that's kinetics, rate. The faster product is formed faster. I mean, that's not right, is it? The less stable product is formed faster. Let's turn over and look at the reaction coordinate diagrams for both of these reactions. This is the exact reaction. This is just showed sort of condensed here. Okay? We have a transition state leading to our intermediate. One intermediate. Common intermediate. It sounds like it's two different things that are in common. It's one intermediate. Okay? Maybe just, it's more clear. Okay? There's your intermediate, right there. One thing. Now from there, the Br minus adds. If it adds here, that gives the 1,4 product, which is the most stable in this case. And so, if we look at these end products, you see how the 1,4 product is more stable than the 1,2? It's lower in energy. So indeed, that's thermodynamic product. But if we look at it, look at the transition states. The transition state leading to the more stable product is actually higher. Now, I showed you this when we did reaction coordinate diagrams. This was in that handout, thermodynamic handout. It's higher, and that's an oddity. Usually the lower your species, the lower energy leading to it. This is odd. The transition state for the least stable product is actually lower. So, which way is the reaction going to go? The fastest. you're gonna roll a marble over a hill, is it gonna go over the small hill faster or the big hill faster? Okay? The path of least resistance is your faster route. So this is your faster route, but the faster route leads to the least stable product. What conditions give the least stable product? Cold or hot? Cold. Cold temperature gives the 1-2 direct addition. Cold temperature means minimal amount of heat available. Minimal amount of heat, so I can't even make it over that hill. That's the idea. I don't have enough heat to make it over that hill. I just make it here, and I fall here, and that's all you get, because if that's all that can occur, then that's obviously the faster reaction.
So does this add heat to the system, which then gives it 100 or something that's...
The question is, why come when we heat it, do we get the more stable product? If there's a lot of heat, is it going to prefer to go over? No, it's still going to prefer to go here. Why, when we heat it, do we get the more stable product? Anybody? Joe?
Is it because the heat excites the electrons?
I can't hear. Barbara?
Is it because the heat would excite the electrons and allow them to make the resonance structure faster? That's not really-
Make the resonance structure faster? No. Resonance is always there. As soon as the H added, we got a pink intermediate. As soon as the H added, we got this. There's no going between resonance structures. The problem is I can't draw pink, so I drew you red and white and said, hey, it's really pink. There's no making it do resonance. Resonance is just there.
But they're all sitting at the higher heat level and then have a greater energy gradient, so that's a driving force. Take with the 1-2.
Basically, with heat, you go here. This is always the faster. But with heat, the reaction is reversible. We can go back uphill. We can actually go back uphill and then we can drive it over that way. Now, with heat, we actually can go any way we want. And when you start going any way you want, you're no longer dealing with kinetics, you're dealing with thermodynamics. You're dealing with, okay, how are you going to decide? If either one can form, you base it on which is more stable. That's more stable. The reaction goes this way, you probably form this, but with heat, it can go backwards. How does it go backwards? I erase it. What would have to happen for this to go backwards?
Have to have enough heat.
And so the bromine adding, the bromine would have to leave, okay? We'll be seeing halides leave. Have you ever seen a halogen leave something? Sure, you put HBr in water, the Br will leave the H. Okay? Brs can leave carbons also. It goes backwards, you push it over, and you set up an equilibrium. Whenever you set up an equilibrium, how do you judge which side is favored? The more stable side is favored. Which is more stable, the 1-2 product or the 1-4 in this case? 1-4. Okay, here's a take home. With cold temperature, you don't have enough heat to form the more stable product. It just goes to the least resistance. With heat, you set up an equilibrium. It goes back and forth. You drive it over, it goes all which way. How do you decide when you set up an equilibrium? Most stable. And the most stable, it's all going to equilibrate, and you're going to end up with this down here. But at that point, is this the fastest? No, it's not the fastest. It's the most stable. Fastest is this one. You only get that one at cold temperature. At cold temperature, you cannot establish the equilibrium. 1,2 addition, 1,4 addition. Which is the most stable product? Which one?
1,
1,4 in this case. For some reason, you guys always think 1,4 is the most stable. Always. No, in this case it is. What's the most stable? Tell me a more general way to tell which is the most stable. More substitute is the more stable. In this example, it was the 1,4. Okay? Why does the 1,2 have the lower transition state energy? Because right here. Let's go back to what happens here. When this attacks the H plus is here, right? And this attacks the H, and we get this, right?
They're the same transition state.
What do you mean they?
1, 2, and the 1, I mean, there's the same, but that was what we just described.
The 1,2 and the 1,4?
Well, there's no 1, 2, and 1, okay, guess so.
You're talking about the first step?
The transition state, or
The,
the first step? Okay, maybe not.
the first step is the same for both reactions. Both reactions begin with this. Yeah? Okay. Well, why is the transition state lower for the BR attacking here? That's what we showed on the graph, right? Well, when the H plus is here, where's the BR minus? Most likely.
Next.
Next to it, because charges attract. Now, it's not covalently bound, we know it's ionized, but the BR minus is next to it. Trust me, they're not going to separate much, and wherever that H goes, they're a tag team, even though they're not covalent. Now, when the H is here, where's the BR? Where do you want to draw it at? It's still here. It's nearby the H that was added. Now, if it's here, let me draw it over here. It's here. Which is going to be faster? Attack here or attack there? It's faster to attack here. So we could say easier. It's easier to attack here because it doesn't have to travel cross country to attack over there. Traveling cross country raises the activation energy and makes the activation energy leading to the 1,4 product higher. It's called a proximity effect. The BR is over here, so it's easier to attack. And so the transition state leading to the 1,2 product is lower. It takes more energy to go cross country. That's why the 1,2 is fastest. But it's not most stable. At least not in this case. Okay. Now, we pretty much have already done the closer look. HBr, low temperature, you get the kinetic product. That's always formed first and fastest, no matter with heat. But if you heat, what can happen is the BR can leave. Mechanistically, you just show that leaving. What do we call it when the halogen just leaves? General term. Ionization. Right? You put HBr in water, what does it do? It ionizes. The Br just leaves, and you make H plus Br minus, right? Well, halogens can also leave carbons. And we'll do more of this as we move forward. Ionization, promoted by heat. Why? Because one molecule is going to two, that and the Br. It's entropy driven. But it forms a nice cation. What type of cation is that? Resonance stabilized. It looks like it's secondary and primary. But it's really a delocalized blend. Which is major?
Secondary.
Probably that. It's actually probably more positive here. But then the Br minus can attack here and you get that product. See, that all becomes an equilibrium. I mean, that can come off, and you can go back here. Once an equilibrium is established, your most favorable is preferred. And that's most favorable because it's more substituted. Okay, let's do some more examples of this. Any questions? So if you take this, let's throw a methyl on here. In the previous example, both alkenes were the same. No matter which alkene you reacted, you got the same product. Symmetrical. This one's not. This alkene has a methyl. If you do HCl at cold temperature, which product's going to form? First off, just state in terms which product's going to form.
Kinetically favored.
Which one?
Kinetically favored.
The kinetic product. At cold temperature, your kinetic product, yes. What's the kinetic product when you're doing conjugate additions, or 1,2 versus 1,4?
1, 2.
Lucy, what's the kinetic product? It's the 1,2 addition product, okay? Previous page, it says kinetic. Right?
Yeah, so how do you decide which one's 1, 2?
Do what?
How do you decide which one's 1, 2 in that situation? It would be the,
Right? Kinetic product, form faster.
yeah.
Okay. Well, which one are 1,2 products? We're looking for the 1,2 product, right?
So,
We'll do this mechanistically, but let's do it just, okay, this way. What's 1,2? Where's the new H at?
The end
on that, and
It's there. So is that a 1,2 or a 1,4?
1, 2.
It's a 1,2. Where's the new H?
The end
2 there, 2. The new H is there. What is this?
1, 4.
1,4. What is this? Where's the new H? It's right there. So what is this?
1, 2.
And what is this? There's a new H here. Okay? Kinetic gives 1,2, so which one does it give? First or third? Here's where we have to do something a little bit new. But that you should have gotten from the previous discussion. So, how do we do this? These alkenes are not the same. You've got to decide which alkene is going to be most reactive. Well, here's your answer. You're going to make the most stable cation. In the first example, there was not, but there was only one cation, and that was this. We can get 2 different cations here. If this alkene reacts, or we're going to make cation on left or right?
Right.
Right. And that's going to give UH there, here. You're always going to make cation on the internal carbons so you can have resonance. Now we can do resonance. We get that. And there's your intermediate. It's one thing, right? We could do a hybrid, but instead of doing hybrid, let's discuss it like this. This is a cation that has character of both of these resonance structures. What type of character does this have? This is secondary cation. And what type of character does this have? Primary. Now the true cation is a blend of these. What if we reacted the other pi bond? First off, would we put cation on right or left?
Left.
Left. And that would give UH there and cation there. But that's a fake structure because we know that this other structure contributes to the true structure. And that looks like that. We have two different intermediates to choose from. Which one we're going to get the better one? Which one's better? A cation that has characteristics of primary and secondary, or a cation that has characteristics of primary and tertiary? Which is a better cation? The one that has characteristics of primary and tertiary. So this is your preferred route, and we're going to disregard this. Now from those you get either 1,2 or 1,4 addition. Since we're cold temperature, we're looking for 1,2. So the chlorine adds really to which cation? Right here. Chlorine adds here. Because now the H is here and the chlorine's here, 1,2. And which product does that give? First. So that's your, so this is your 1,2 product. For that reaction, we could ask this. Of the other three, which one is the 1,4 product of this reaction? Ashley, which one's the 1,4 product of this reaction? Do what? No. How do you get the 1,4 product from our two resin structures? The chlorine adds to which cation? Over here? Chlorine adds here? Why? Because it's 1,4, right? That's 1, 2, 3, that would be 4. Chlorine adds 4. And if it added there, which one would we get? You get that one. There's your 1,4 product. These two would come from these cations. But guess what? We don't get these cations because they're not. That's not the most stable cation. You don't get these. This gives the 1,2 product. Cold temperature 1,2 product, kinetic product. It's going to be the fastest. And without heat, it's not going to equilibrate. Okay, do the next one. Run you guys on my left do the first one, HI. You guys on my right do the next one is HCl. Unless you have a symmetrical diene, you've got to consider which cation is going to react, just like we did in that example. You got the first one, Zach? Or Jordan on the board?
You just want the product?
Just product.
Yep.
That's kind of an ugly bond angle. I'm going to draw the I-9 down. Just so it has more of a zigzag. Okay, where's the new H in his structure? There's 2 on the end, there's now 3 out there, so there's a new H out there. So it looks like you did a 1, 2, 3, a 1, 4 addition. So it's clearly a 1, 4 product. Let's see if that's what we get. If I react this double bond, I would get cation on left, and then I can invoke the resonance windshield wiper over. Resonance arrow. Just about everybody left out the resonance arrow on the test. I didn't count off because we haven't officially covered resonance, but on the mechanism, the first mechanism, there's resonance. It says use appropriate arrows. That's a resonance arrow. That's your appropriate arrow for showing resonance. Moving forward, you'll lose points for not showing appropriate arrows. Boom. Boom, boom, boom. H. Windshield wiper over, plus here. Is that right? So if we react the right double bond, we would get this cation, one cation, right? Has characteristics of tertiary and secondary. So that's the A possibility. If I did the B possibility, I would get new H there. That's an ugly bond angle, but I'll draw it up, try it up. Plus here. Then we can windshield wiper over, and we get resonance structure that looks like that. New H is here. That's one cation, right? True structure is a hybrid, but it has characteristics of secondary and primary. Would you rather make a cation that has secondary and primary characteristics or tertiary and secondary? It's a better cation. Don't do that, Ruth. Forget about it. That alkene is going to react initially. Now, this is your choice. If the iodine adds here, that's your 1,2 product. 1,2. If it adds here, that's your 1,4 product. Which product are we going to get with heat?
1, 4.
Not always. Which product do you get with heat? You get the most stable. Which one's the most stable in this case? There's the 1,4. If it added here, you would get there's a new H out there. This is your 1,2 product. Which is more stable, 1,4 or 1,2? 1,4 product. Why? More substituted, okay? Indeed, that's your product with heat. A more stable product coming from this cation. Okay, down here, cold, which product are going to be? Now down here you could actually say, is it 1,2 or 1,4?
1, 2.
Yes. Because the kinetic product is always 1,2. Why? Because the H added here, that's where the BR is or whatever, boom. It's closest to add 1,2. 1,2 is always kinetic. But thermodynamic is not always 1,4. It can be either. We just got to decide which cation we're going to react. If I react with this cation, does anyone want to draw it on the board? Somebody? Michael?
You want to draw just the final one?
Product, yeah, just the product. Okay, did you draw a 1,2 or a 1,4 product? Where's the new H in this structure? On the end. So this is a 1,2 product. Check. Okay. Well, that's what cold temperature gives. But there's actually two possible 1,2 products. We have to decide which alkene is going to react. If this reacts, we get UH there and plus here. And this appears to be the double bond that he ultimately reacted because Cl minus adding there gives that product. And that's secondary. We can do resonance, windshield wiper over. And the resulting is going to be what? Tertiary. So that, reacting that one gives a cation that has secondary and tertiary characteristics. If we reacted this one, somebody tell me, just by envisioning the resonance structures, what's the cation going to be?
Tertiary, and primary.
It's only going to be two cations. Where's the cation going to be, Taylor? If we reacted here, we would make two resonance structures. What would the cations be?
At the tertiary one?
Tertiary. One would be tertiary, the other would be primary. That gives tertiary primary. Does everybody see that?
So the other tertiary would be if it finds the other way, correct? Because there are two ways that bond could break, right?
Would you rather make cation as tertiary secondary or tertiary primary?
Obviously tertiary.
Connor?
Tertiary, secondary.
Yeah, forget about it. We get this one. What product do we get? 1,2, chlorine adds here. Here's your product, 1,2 product.
My question is if that alkene goes to gets the hydrogen and forms the tertiary carbocation at that top methyl group off the thing, and there is no resonance structure. How does that factor in, or is that not so heavily unfavorable?
You're certainly not going to form a non-resonance stabilized cation.
Okay.
A non-resident stabilized cation is not going to be preferred over a resident stabilized cation. Which is better? Tertiary and that's all you got, or tertiary and primary with the resident structure? This is better. Right? Charge is delocalized. Tertiary, secondary. That would be tertiary primary. If you don't see that, you need to work on your resident structures. Okay. 1-2 products, so there you go. There's your 1-2 product. Questions about those two? What if we did the same reaction with heat? What would the product be? That's the same reaction as there. What would the product be?
So it'd be from the same one, but on the tertiary.
What would be the product with heat?
Seal on the tertiary carbon.
Anybody else?
I guess
Would it
that
be the
one's
same?
still the most sensitive.
Elena?
Would it be the same?
Yes, same product. This would get the same product. Same exact product. Questions about that one?
Why?
Why would it be the same?
Most substitute.
Well, the 1,4 product would come from chlorine added here. And if chlorine added here, you would get this product. There's the 1,2, here's the 1,4. Which one's more stable? Because heat gives the most stable. Which one's most stable, the 1,2 or the 1,4? It's probably more stable. Why? It's tetrasubstituted alkene. This is a trisubstituted alkene. This is an example where the 1,2 product is the most stable. Everybody see that? Please don't fall in the trap that heat gives the 1,4 product. A lot of books will tell you that. That's because they show you simple examples. Heat gives the most stable product. Which is most stable? The one over there? It's all based on alkene substitution. You can do those at the below. I mean, we just answered what the question, this question down here. Sometimes the 1,2 is the most stable. Any questions about 1,2 or 1,4 additions? Y'all have a late night last night? I seem a little low energy. You did some finger exercises? 3rd grade? You warmed up? Let's look at Diels-Alder reaction. It's our next reaction of dienes. Diels-Alder reaction won Nobel Prize in 1950. Diels and Alder. Great combo back in the 50s. You had Dean Martin and Jerry Lewis. Mickey Mantle, Yogi Berra, and you also had Diels and Alder. The Diels and Alder is a conjugate addition reaction. The bigger, this is not really my writing here. Here's the simplest example of a Diels-Alder. It involves a diene, we're doing diene chemistry, a diene reacting with an alkene. So two double bonds, two alkenes reacting with one alkene. Now this is the hard part. This is 4 carbons, and that's 2. And 4 plus 2 is 6. Okay? 4 reacts with 2, and you make a ring, and the ring is a 6-membered ring. Diels-Alder gives a cyclohexane, but it's going to have 1 pi bond in it. Diels-Alder always gives a cyclohexene. Okay? Always gives a cyclohexene. At least 1 pi bond. It may have 2 in it. And of course it may have decorations on it. Like substituents. But that's the basic, 4 plus 2. It's called a cycloaddition. And I don't think I see that term up there. We'll see it somewhere out here. Cycloaddition.
Further down.
Cyclo, do what?
It's further down the page.
Cyclo meaning cyclic. You're making a ring. And they're adding to each other. Cycloaddition is a very general term. There's actually lots of different types of cycloaddition reactions. They involve a cyclic transition state, which is called pericyclic. It's even a more general term. There's probably a chapter in your textbook on pericyclic reactions. Okay? Let's go ahead and move arrows. Reaction mechanism arrows, which show what? Movement of all electrons. Showing how bonds are broken or formed. How do we get this over here? These electrons move here. Okay? They go over there and make a single bond over there. Something's got to leave this carbon. These actually leave and go up here. So these, when something comes in, these swing out and go up here. But now something has to leave that carbon. These come down and fill the void where that left. So you got 3 arrows here. All that happens at the same time. And believe it or not, that leads to that, right? Because what does this arrow mean? Hinge over, we make that single bond right there. When this comes up, we're making a single bond up here, and that turns into single itself. So we made that bond, and that becomes single. What does this arrow here do? That's hinging down, and that's where your double bond is. And that hinges down. All these arrow movement takes place at the same exact time. It's a concerted transition state. And that's your Diels-Alder mechanism. 4 plus 2, cycloaddition, concerted. We can envision this, it's basically overlap of p orbitals. It's like a pi system. But it's not within one molecule. If it was within one molecule, we would call it resonance. What do we have here? Don't we have 4 p orbitals? And that's pi bond, and that's pi bond. Of course, there's overlap here. What happens is the other molecule approaches. I'm going to draw these p orbitals sort of like this. But isn't that also a pi bond? What happens is these approach close enough to get reaction, and this starts overlapping. And that starts overlapping. And now you have sort of a transition state, which probably will show in the book. But the electrons have to sort of sit somewhere, and ultimately this becomes bonded, and the electrons end up sitting here while these become bonded. So it's all p orbital overlap in your transition state. We show it like this, and that's your output. Question?
So the reason that this reaction actually happens, the input of P, is Is it because cyclohexene is a more stable structure? So they will.
Let's evaluate it, okay? We can pull out our calculator and do some bond numbers, but let's evaluate it more qualitatively, just in general. What was broken over here? And what was formed? I see 3 pi bonds over here, I only see 1 over there, right? So what's broken?
5 sigma.
Everybody agree 2 pi bonds are broken on this side? What's formed over here?
Sigma.
2 sigma are formed. So which is better thermodynamically? 2 pi or 2 sigma? 2 sigma. If you see that this is going to be exothermic, if you do a calculation, you'll see, because you've got stronger bonds on that side. Okay, so it's driven thermodynamically. Is it driven by entropy? Two molecules combine into one, is that driven by entropy?
No.
No. Not driven by entropy, but it's driven thermodynamically. Would you want to heat this reaction? Do you want to just heat it as high as you can, or is that going to hurt?
It must be a certain.
What do we say about entropy? Entropy is not favored. If you heat, you're going to magnify that term.
If you get too high, it starts favoring entropy.
Which side is entropy favored?
The reaction.
Yeah, if you heat this, it's going to go backwards.
Don't you need some heat for the reaction to happen?
You need enough heat to get over the transition state. If you heat that reaction, which side's going to be favored? It's dry material. Yeah. See, you got to understand this. You need enough heat to get over the hump. When I say heated, I'm talking about heated in more than you need to. For example, if this is 50 degrees, I don't know. If that's 50 and that's all you need, if we do it at 100, is it going to be even better? No, if you start getting too hot, it's going to want to go backwards. Because going backwards is entropy favored. And if it goes backwards, what do you want to call it? It's called a retro Diels-Alder. And such things can go backwards. Yeah, if you heat that compound over there to like 500 degrees, I guarantee you, you're going to form these two over here. It's going to go backwards, entropy driven. Okay? That's basically just keep going back to your Gibbs free energy equation. What it ultimately means is how you use it to evaluate reactions. Right? Did you do that in Gen Chem? When you learned Gibbs free energy? Hasn't been that long since Gen Chem had it.
So
Okay.
you go from 2 molecules to 1, do you normally lose one total degree of unsaturation? Is that standard? It seems all thicker.
I don't know if that's standard. I mean, here you are losing 1 degree of unsaturation, but I don't know if that's always the case. Okay, you can also do this with a diene. That's a diene. What do you want to call this guy? Well, here's a hint. It loves dienes. That's called a dienophile. Okay? Does it say that up there? Yeah, that's the thing that likes dienes. So Diels-Alder is a diene and a dienophile. The dienophile is usually an alkene, just one. Okay? You can also do this with triple bonds. If this added here, this up, and this down, you'd get your 6-membered ring, pi bond here, but there'd be 1 pi bond left over here. So there's actually 2 pi bonds there. Alkynes can also be dienophiles. Now let's look at the dienes a little bit. There can be a variety of dienes. The simplest is just butadiene. You might want to call that 1,3-butadiene, but you don't need the 1,3 because there's no other way to put the double bonds in. So it's just butadiene. You could have this here with a methyl, of course. You can also have dienes that are in rings. Now, importantly, your diene has to be in the S-cis form to react. What do we mean by S-cis? The S stands for single bond. About the single bond, see how that's the single bond? The double bonds are on both sides of the single bond. As opposed to a structure like this, where that's called S-trans. Because if that's the single bond, one double bond is there and one double bond is here. The diene must be in the S-cis form if it's going to react, because you've got to make the ring. Okay? So this would have to rotate. These guys actually react fast in Diels-Alder because they're stuck in the S-cis form. See how your double bond is both sides of that single bond? And because they're in the ring, they can't rotate away. These guys actually react very fast in Diels-Alder. They're always ready to go. Now with your dienophiles, on the previous page we just showed a simple alkene. But typically, the dienophile alkene has an electron withdrawing group bonded to it. Such as this. So this would be an electron withdrawing group. Obviously we got a dipole, and that makes dipole here. That helps polarize the pi bond. The reacting pi bond. And so there's a variety of examples. Here's one with two groups. The two groups are trans, but the two groups can also be cis. You can also have cyclic dienophiles, and there's an alkyne. We'll come back to this polarization thing here. Let's first look at stereoselectivity. Some examples. This reacts with this, you get this product. How does this happen? Well, it's 4 plus what? 2 equals 6. Electrons here, electrons here, electrons here. There's your 6-membered ring. But these two carbons have the ester groups on them. They're cis and planar. Now these carbons are tetrahedral. And so now we have an opportunity for these to be both forward or one forward and one back. How's it going to be? Cis. Why is it cis? Because it's cis over here. Connor?
Why could they not both be back?
Okay, let's draw them both back. That's not bad. Can it be like that?
Yes.
Yeah.
Same one.
Sure it can. That's the same molecule. Why is that the same? They are, so why are they superimposed? How do you know that?
It's just like you're looking at it from a different.
You can take that and flip it over, and then both groups will be coming out and we'll superimpose. But how do you know that? What's the trick of knowing that that's going to be the case? Planar symmetry. Has multiply symmetry, so the mirror image is the same thing. Okay, you can draw it either way you want, it's the same molecule. It's like drawing a hand up there with the thumb that way or the thumb this way. It doesn't matter. They're both the right hand. Or in that case, it's really not a hand at all. Okay, this is pretty easy. Cis here, cis there. Why? We're not really going to look at the exact details of why. But because it says a concerted reaction and everything just boom happens, the groups don't have a chance to turn. They're just that way. We're not going to look at it any closer. Cis, cis. Alternatively, if you react this with same molecule, but here they're trans, they're going to be trans in your product. Okay? Your stereochemistry is maintained in this concerted reaction. Let's look down here. Here's some examples where we have different stereochemistry and the diene. Here, believe it or not, you have stereochemistry. Both alkenes are E. When you zip these together, 4 plus 2, you get this. There's going to be a pi bond over here. Your two ester groups, there it's linear. Now it's organoplanar, but they're in the plane, so there's no cis and trans there. These two carbons are tetrahedral. How are these methyls going to be? They're going to be cis. Why? Because your alkenes were the same. Okay? Same alkenes, same side. Again, we're not going to look at why. But it all has to do because of the concerted nature. I'm not telling you the full story. We're just basic stereochemical outcome. Look at the difference. Here you have a diene, but that's E and this is Z. So these are opposite. When this sits together, you get the same product, but your methyls are opposite side. So your stereochemistry is actually easy, or easier than what the regiochemistry we're about to look at. Whatever you have to begin with, you're going to maintain in your product.
How's this cyclo S-cis diene reacting with the regular alkene? The one that said it was stuck in S-cis conformation, so it's more reactive.
We'll do some examples of that in a little bit. Now let's look at regioselectivity. Regioselectivity is a bit more involved. What do we mean by regio? Well, different possible constitutional isomers. Look at this example here. We have a diene and a dienophile. We could zip this together like this. And if this was oriented like this and that, which product would we get? Scott? Which product would we get, left or right over there? Yeah, this would give this because the methoxy is down, right? This carbon with the methoxy would be bonded to that carbon, and in the upper carbon we have the ester. Gives that. But see, this could also be, we could flip this over and have this up, keep this the same, and if we zipped it together like this, 4 plus 2, this carbon and this carbon are bonded together, so the groups, the substituent carbons are bonded together. We get that. And those two are regioisomers because the groups are bonded in different regions in the product. Which way is the reaction going to go? Which is the regio chemistry we expect? We have to consider polarization. of this guy here. Really of both of them. Remember I said that the alkene would have an electron withdrawing group to polarize this? Let's show resonance structures of this. Why don't you do it on your own while we take a 3-minute break? Show resonance structures of this molecule. We need to show 2 resonance structures. Okay? Show 2 resonance structures. We're going to look at the hybrid. So in resonance, we talked about delocalization in neutral compounds with heteroatoms. That's exactly what we need to do here. Have a precessional frequency. That's what a nucleus does when we do NMR in organic too. Because a nucleus with a net spin, it has a net spin I can't spin it fast enough, but it's, in addition to that spin, it's also slowly doing a precessional spin. That frequency, we can match it with some light to get an absorbance. I've never done this before, but I've seen it. Also, the important thing here is that this thing doesn't just spin like this, it spins with an angle. See how it's tilted? You might think it's because of the way the string is, but it doesn't spin flat, it spins with an angle. These types of things are important for understanding the consequences of that, and why you get certain phenomena. neutral molecule. Can you draw resonance of this? Well, we have pi system here. Here's your pi system. 4p orbitals. But at the end of that hose pipe, you've got an oxygen which likes to pull all the water towards it. So we can move those electrons towards that greedy oxygen, and we can get that there. But now we have a cation. How do you stabilize a cation? Move electrons towards it. We can move these down, but that just gives you back what you started with. What else could we do? We could windshield wiper this up, and this gives that resonance structure there. So there are your two additional resonance structures. Now let's draw the hybrid. What type of bonding do we have between the C and the O? Double, single, single? What's in between double and single? 1.5. What do we have here? Single, single, but some double bond character here. So what's in between single and double? So we're 1.5. It's not perfect blend. What do we have over here? Double, double, but then some single here. Yeah. Okay, you see? Charge. What's the charge of the oxygen? Negative, negative, and neutral, making it just partial negative. What's the charge of this carbon? Partial plus. Importantly, right here, of the two carbons that react to this species, which one of those did I circle? Which one is partial positive?
The bottom.
Neutral, neutral, neutral. I never see that carbon take on any charge. But right here, the bottom one takes on positive. So it has partial positive, as seen from your resonance structures, as seen from the polarization of that oxygen. Very important. Partial positive right there. But that's always going to be the case with these guys. This is a broad term which we'll see more in organic 2. It's a carbonyl compound. The first carbon off of your carbonyl is called alpha, and the next one is called
Beta.
beta. And there's unsaturation between the alpha and the beta carbons. You call this an alpha-beta unsaturated carbonyl compound. In all of those types of compounds, the beta carbon will be the one with partial positive. Because you'll always be able to do the resonance structures right there. So if we go back, and it's the presence of this group that polarizes the alkene and gives you your polar partial positive. But that's what we said over here. The electron withdrawing group makes it more reactive and Diels Alder. Why? It polarizes the double bond. I showed it right here. But all of these have partial positive. Now this it's both. That's symmetrical, so it really doesn't matter. Which carbon's partial positive? The beta carbon. At the end of organic 2, we do Michael reactions, and you have to know that beta carbon is the partial positive. Right here. So, we identified partial positive. In the dienophile. Now in this guy, we're going to need to identify a partial negative. And once we do it, we want to make sure what does that say, partial net minus? Must be partial plus, right? Okay. We need to identify a partial negative over here. And once we do, we want the partial negative carbon to bond to the partial plus carbon, and it will be done. We just need to do the same thing over here. Draw resonance structures of this guy. let's identify, now it's either this carbon or this one, because those are the ones that react. We know that's partial plus. Which one is partial minus? Well, here we need to do resonance structures. How do you do resonance structures of a neutral? Especially when there's lone pairs, you want to start where? Start with the lone pairs. These can move here, these can move out. Now we have double bond there, one lone pair left, positive charge, minus here. Now we keep going. How do you stabilize a minus? You can either move it here and move these out, but that gets you back there. Can we move them somewhere else? We can move them in here and move these out. It gives double bond here and minus there. Now what's the true structure? It's a hybrid. Let's draw the hybrid. We've got double bond, and single. What's the blend of that? Bond and a half. We've got single, single, and double. What's the blend of that? Bond and a half. We've got single, single, double. Bond and a half. We've got double, double, single. Bond and a half. Charge. Oxygen, positive, positive, neutral for partial positive. Where are the other two? Hold on, that's not partial positive. Yes, it is. We've got a neutral molecule. I'm like, okay, yeah. It's neutral molecule, so it's net neutral. Yeah, that's positive. Here. Now, up here, we made negative. Which carbons have partial negative? Well, obviously, that one. And that one. So it's partial minus there and partial minus there. There's your hybrid with partial charges delocalized. Of the original carbons, of the reacting carbons, the 1 and 4 that react, which one has partial minus? Obviously that one, as shown in your hybrid. So now that we know that's partial minus and that's partial plus, we want these two carbons to bond together. So, is it going to bond as drawn, or do we need to flip this over? We need to flip it over, right? Flip it over, that's partial minus. Line these up. That's partial plus. We want these two to bond together. That's the goal, to get the two with the most charge. That's going to be the most attractive to each other. You see, when these molecules butt up against each other, okay, and I've got a negative portion, okay, and okay, you guys over here, I'm going to react with you. I got a negative portion. Hold your arm up here. All right, and you got a negative portion. Are we going to react like this? No, I'm going to flip and react like that, because the positive is going to react with negative. These guys are going to, we want to make sure they line up. Now we can zip it together. And which product do we get? We get that one right there. Okay, there's two below for you to do on your own. In the end, partial plus, right? Those are always easy. Always a beta carbon. These over here, you're going to have to do some resonance structures to identify the partial and negative. Please do those first. Choose from below. You need to supply the answer. There's no stereochemistry in the above examples. This is really a repeat. We've already done this. It's really a repeat. I think because one sheet is mine, the other sheet came from the internet. This sheet is mine here. What's new? Here we go, right here. Show the product of that reaction. What's the deal? What are the two components of the diazole? A diene and a dienophile, which is an alkene. Do we have the two components? That's a diene. Give me the dienophile. 4 plus 2. What I'm trying to get at here is you're not always going to see the diene drawn like this. Maybe the diene will be drawn like that. It's not always going to be drawn like this with like neon lights flashing. Diazole, diazole. You may have to draw it in the, what type of conformation do you want to draw this in? S-cis? Yeah. Draw it in the S-cis form and then do your reaction.
You can do that.
You can do what?
You can just redraw, rebond them, or
No, you just draw a different conformation. You want the S-cis conformation. Back when we were doing Newman's, we were doing like gouge conformations and anti-conformations.
that's a locked in,
This is locked in?
is it not?
Well, explain. You may be onto something.
I mean, it's in a one plane, so that's actually here, that the two alkenes are, what do they be? So, I guess I might do this.
No, if you go back in the two forms, what happens when this goes to this? Pretend that bond is there in the alkene. This bond here just has to rotate. And the alkene comes over here. That bond has to rotate. Can that bond rotate? Looks like a sigma bond. Can sigma bonds rotate? I mean, if I had a sigma bond here, remember how I spin it? What if it's like this? Can I spin it? Well, here the double bonds are opposite. Can I spin it and make them both like this? A true sigma bond you can rotate. I thought you were going to ask, why does it rotate since there's some overlap between the 2 and 3 p orbitals? That'd be a good question. It actually is not enough overlap to restrict the rotation. Rotate. You would need to rotate it. Oh, you got to put it in the S-cis form. So I'm just going to draw this like this. But this double bond is trans, or what's that, E? And this double bond is Z. One is cis and one is trans. So that one I'll draw like that, and that is E. But this one I'll draw like this, because it's Z. These are the same thing. But then when I zip it together, well, it's over there, but I zip it. Do I need to flip this over? It'd be the same thing. Let's look at it. What do we get? get a 6-membered ring with a cyano here. Where's the pi bond at?
Right there.
Here. Where are the phenols at?
1, 4.
1 and 4. So phenyl here and here. Now those are tetrahedral. They're going to be forward or back, or they're going to be cis or trans. They're going to be trans. Now what you do not know here is the relationship between that and this. You don't know that. And we're not going to go there. But there's your problem. If we flip this over, would it give a different problem? No. It still have a 6-member ring with phenols at here and here. That reaction does not have any regiochemistry in it. There's only one way to zip it together. If you don't believe me, try to draw another 6-membered ring product. The only question is, are the phenols going to be cis or trans? But we know the alkenes are opposites, so they're going to be on opposite sides there. Let's do these down here. Product here. Here we have a diene that has, it's part of a ring. Okay? And I've just turned it so the double bonds are ready to react. Whenever you do these with the ring, just ignore sort of that part. And then at the end, put it back in. It doesn't do anything. So we zip it together, what do we get? 4 plus 2 is 6. Double bond here. There's a cyano here. But what did we ignore? It's a CH2 that's between carbons 1 and 4. It's a CH2 bridge between 1 and 4. Well, that's carbon 1 and 4 right there. Well, guess what? It still has a CH2 bridge. We can draw that like that. And that's it. It looks a little odd. But what it is, it's a 6-member ring with a steeple between carbons 1 and 4, a CH2 bridge. Okay? So whenever you have these cyclics, just ignore the cyclic portion and put it back in at the end. Now, if you draw the ring flat, the bridge is actually either out or back. But I'm not really going to say much about that. You could just draw it as it did originally. And if you bold it, it's like that bridge is coming out. You can make a model of that if you want. You'll see how the bridge is like a steeple. Okay? This is an example with this part being cyclic. Still the same thing. Zip it together. 6-membered ring. Double bond here. But we just have, I can't draw these straight. Looks funny now. Coming off of these 2 carbons is the carbonyls. This is now tetrahedral. Are these bonds to the carbonyls going to be cis or trans?
Cis.
So the cis here, they have to be cis, it's in a ring. But they are cis, and so they're going to be cis here. These 2 bonds are cis there. Remember, all your stereochemistry is maintained in your Diels-Alder reactions. down below, this is called furan. It's just like this. Instead of a CH2 bridge, it has a oxygen bridge. Show the product. Biggest producer of furan in the United States, General Mills. They make your cereal like Post or Kellogg's, General Mills. They also make Puree.
If it's easier for us to draw it, that's crazy.
Furan usually will be drawn like this. Furan's aromatic, we'll see it in organic 2. I just got to turn sideways, so now we can zip it together. Furan's actually a good dyeing for a Diels alder. Zip it together, you get a 6-membered ring. There's an ester here, double bond here. What do we have connecting 1 and 4? Oxygen. Oxygen bridge. You get it? Right? Just ignore it, put it in at the end. Ultimately, it's the 2 pi bonds reacting 1 pi bond. Zip it together, everything else. Furan. Furan is, first you get furforaldehyde. 5 carbon sugars are converted to furforaldehyde, and that can be decarbonylated to furan. Why does General Mills got a lot of 5 carbon sugars? Because they deal with corn. All the corn waste they convert to chemical instead of putting it in the trash. Fructose, 5 carbon sugar.
They sell it off.
Yeah, they sell it to, yeah, that's how they recycle their corn waste. Convert all the fructose to 5 carbon furan and then remove 1 carbon to get the 4 carbon furan. That reaction right there is used to ultimately make this compound over here. You see the 6-membered ring with the alkene? Anytime you see those can be made by Diels alder typically. Got lots of decorations on it. But made, that was on the test, wasn't it? The structure? That was one of the top of page 4. Anybody know that drug? It's also on one of the hormones. What's that drug, Ashley? Yeah, it's Tamiflu. Yeah, made starting with a Diels alder reaction. Yeah. Product down below. You got hole punch. That's just the rest of the ring. What's the product? Oh, you were reading right there, though.
You told him.
I was thinking, how did you know that?
Yeah.
Questions?
Can it react? Can that compound react?
I can't hear.
Sorry, can that compound actually react?
Ah, good question. Can this compound react as a diene in a Diels alder?
'Cause you can't-
What form does it need to be in? S-cis? Can this become S-cis? It's stuck in the S-trans form. Can it react, Newton?
No.
It cannot react. No reaction at the bottom. The diene must be in the S-cis form. If it's stuck in the S-cis form, it's going to be highly reactive. No reaction. Don't look on the back. It's the answer key to the previous. We did most of them. I put it in upside down so you would not be easily looking at it. There's also a t-shirt that cut me on dime. And organic chemistry humor is good stuff, ain't it? There's the synthesis of Tamiflu. It's actually some other stuff there. All these reactions. Boy, we just covered the tip of the iceberg here, don't we? Lots of other stuff. Some of these reactions you should be able to give a good try. Okay, guys, everybody get a hand up today? So, what have we done? We did resonance. Then we did chemistry of dyes, which involves some resonance, right? 1, 2, 1, 4 addition involves a resonance consideration. Any resonance in the Diels-Alder discussion?
Yes.
Yeah. Next topic is going to be mass spec, our second type of spectroscopy. And guess what? Resonance will also be very important in mass spec. Let's introduce mass spec real quick. Every time we have left. Any questions about dyeing? 1, 2, 1, 4 additions and Diels-Alder reactions. Mass spec here, a little info warm up. Question on the back here. There's 2 alcohols and 2 IRs. Which alcohol goes with which IR? Which alcohol?
Second.
Well, both IRs show OH. Both IRs show saturated sp3CH. They both have fingerprints. I mean, the fingerprints are different. But which is which? It's nearly impossible to tell. Is that right? I don't know which is which. If I had a known IR, I could match up a fingerprint with a known IR scan, like we do with criminals. But if I just found a fingerprint on the desk, I don't know whose it is. Can't tell. IR has limitations. You can tell functional groups, but you can't tell the backbone. Now these compounds have different molecular weight, because this has an additional carbon and 2 H's. If we can determine the mass of these, well, then we can easily distinguish them. IR, though, is... Most of your spectroscopy is complementary. One type of spec gives you some information. You use another type of spec to get other types of information, and altogether you get a complete package of information. You need to do mass spec. That's one thing. Of course, you can also do NMR, and we'll do that in organic too. That's when the nucleus will spin and have a precessional frequency. So what is mass spec? Let's look at the back of the, well here, first off, here's a couple of mass spec. We can introduce this. It's not going to mean a whole bunch to you right now other than just an overview. Once you learn more, you go back and look at this. Here's the mass spec of one alcohol. This would be 1 propanol, OH at the 1 position. The molecular weight is 60, if you add it up. And what we see here is these are going to be all represent masses or molecular weights, and we get a peak at 60. Down below, this alcohol with an additional CH2 has a mass of 14 more, 74. And if you run the mass spec here, you get a peak at, oh, it's quite small. It's almost not there. One important thing we'll see is we expect cleavage peaks. And based on structure, we can expect certain cleavage peaks. Really, we need to come back to that. So we'll start by ending here. Please look at an overview of mass spec, how the process happens, and the idea of cleavage peaks. That's summarized here. You can do some reading in your textbook, and we'll hit the ground running tomorrow with mass spec. Is there SI today? SI is on Monday, Tuesday, and Friday. So there is SI today at noon. Y'all doing hydration of an alkyne in lab? And that lab is going to have mass spec. But your report is not going to be due for a couple of days. We will cover mass spec by the time you get ready for your report. Okay guys, see you soon.